same thing, this one should go to 0, this one should go to 0, so on and so forth, until we only have the point slot. Yeah, yeah. Well, yeah, that's what I mean. And that's what we care about, because that's what we're looking for. I mean, that's the probability that we're trying to find as it goes to infinity.
All right, I guess we should get started. So what I want to do today is talk about combinatorial Hopf algebras. Now, I mean, in a sense, you could argue that a lot of the class, this is what we have been talking about. But what I want to do today is talk about an object that is called a combinatorial Hopf algebra. So it's the following thing. So the combinatorial Hopf algebra. Sometimes people just write CHA. It's basically the kind of Hopf algebra that we have been studying. I mean, you want to think of this as the Hopf algebras that we have studied, where things are induced by combinatorial objects. That's kind of a rough idea, but the formal definition is this. It's a graded, connected Hopf algebra let's call it H, and since it's graded, I can write sum over n greater than or equal to 0 of Hn over some field K. Now, one thing that has been true of a lot of the Hopf algebras that we have studied is that even though they're infinite, they're not that infinite in a sense. And what I mean by that is that actually, when we look at the graded pieces, they usually have been finite dimension. And we're going to demand that out of a combinatorial Hopf algebra, so the dimension of each graded piece is finite for all n. And so far, this is the kind of object we've been studying. But to be a combinatorial Hopf algebra, you need to have a choice of a character. A character alpha from H to your ground field. Okay? And remember that a character is nothing more than a multiplicative function. Well, it needs to be multiplicative, but it also needs to be a linear function. Okay? So this is going to be our definition of combinatorial Hopf algebra, and we're going to denote it by H, alpha. And that's to remember that that the character is going to be part of the definition. Okay? And we've seen many, many examples of this. Let me just talk about a few of them that are going to be useful for us. So we could have H be the Hopf algebra of graphs. Graded by number of vertices. And in this Hopf algebra, we had that we've talked about at least two Hopf algebras of graphs, and the one that I'm talking about here is the one where the coproduct is given by summing over all the subsets of your vertex set, and then you restrict to W, and then you restrict to the complement of W. Okay. And then we also have to choose a character, and as you have seen, there's really many different choices for characters. Any multiplicative function of a graph. Okay? And one easy choice is to just choose the co-unit. You can always do this because the co-unit is always a character. And so remember that here, the co-unit is going to be 1 if the graph has no edges, and 0 otherwise. Okay? That's multiplicative, and so this is going to be a combinatorial Hopf algebra. Okay? So that's one. Another one, I mean, really there's many different examples. Another one is to consider the incidence Hopf algebra of posets. With 0 and 1. And so here, the coproduct is given by summing over elements of the poset, the bottom interval tensor the top interval. Okay? And again, here I could choose any character, and I might choose a different character, which is the Mobius function. Remember that we proved that the Mobius function is multiplicative. And so I can define that to be my character, and that'll be an example. Okay. Maybe a different example is the other Hopf algebra of posets we considered, where the coproduct was given by cutting the poset into two by an order ideal. Okay, so we had I an order ideal. So remember, an order ideal is a downset, and so we considered the downset tensor the upset. Okay. All the ways of cutting the poset into an order ideal and the rest. And here, again, I have a lot of freedom for what my character is, and what I'm going to do here in this case is just consider this character, which is always equal to 1. Actually, I shouldn't call it epsilon. Let's call it just, I don't know, alpha. Okay, so alpha of any poset is equal to 1, and so of course that is going to be a multiplicative function, because 1 times 1 is equal to 1. Okay. Let's talk about a different example. Which is kind of dear to this department. So in this department we like polytopes, and we saw that we can make a Hopf algebra or generalized permutahedra. Okay? These are these special polytopes. So I mean, just to remind you, the coproduct of a particular polytope was given by taking all the subsets of the. So if this polytope is n-dimensional, then we looked at all the subsets of 1 up to n. We pointed in the direction of that subset. So given the subset, we made a vector that had ones where the subset is. And so when we take that polytope, we pointed in that direction, and we saw that whenever we did that, the phase that is maximal in that dimension decomposed naturally as a product of two polytopes. And so those were the factors that we put here. So P restriction to S and P contraction of S. Okay. And here, I could think of several different multiplicative functions. But maybe one that would be kind of fun to think about is that you can consider this multiplicative function. This is going to be the number of lattice points in the T stylet of P. Let's say that P is n-dimensional. Okay. Here, let's say that T is some integer. T is maybe some natural number. Okay. And so my function of the polytope is going to be take your polytope, scale it by T, and just count how many lattice points are in there. Okay. So I can do this, but the question is this a character? In other words, if I have a product of two polytopes to the Ehrhart, this is what's called the Ehrhart polynomial. It's known to be a polynomial function of T. And if you count the number of lattice points in P times Q, you'll see that a lattice point in P times Q is just a lattice point in P, comma, a lattice point in Q. And so actually this is a multiplicative function. Now, if you're familiar with Ehrhart theory, you know that this always turns out to be a lot nicer if you assume integer coefficients. And so that's something we can do. We can just restrict here. Integer coordinates is what I mean.
But that wouldn't be necessary for Aguiar, right? It's just
Yeah, that's right. So I don't really need to put this condition for this to make sense, but it'll be nicer if I put it here, and this will be a polynomial in T as you vary T. Okay. But actually here I'm considering for each natural number T I get a character like this. Okay. And here you can begin to see that maybe, I mean, sometimes the characters are really trivial, but sometimes you actually might want to do something interesting, like make the character actually count something interesting. Okay. A fifth example, which is very important, is QSYM. So these are the quasisymmetric functions. In x1, x2, etc. Okay. And we discussed how the coproduct here is, in quotation marks, just plugging. So if I have a quasisymmetric function of x, then I'm basically just plugging in two different alphabets into the function. And that defines my coproduct. And the character that I would like to define here this one, zeta of Q. And I'm going to define it. Let me define it in two ways. So remember that this is the monomial quasi-symmetric function, where the alphas are some exponents, and actually remember that this depends on a composition. So maybe let me call this M sub C. Okay, so C is a composition, maybe 2, 4, 3, and so MC, remember, just gives you the terms of the form xi squared, xj to the fourth, xk to the 3, where I is less than j is less than k. Okay, and I need to define this, and I'm going to define it to be 1 if C is either, let's see what's the best way to say it. Let's say that it's 1 if Z has 0 or 1 part and 0 otherwise. So if C has 0 or 1 part, that means that it's either the trivial composition, the empty composition, or it's just a composition. So I mean, maybe I'll write it like this. So C is either the empty composition or it's just a single number. Okay, and in that case, you give it a 1. Otherwise, you give it a 0. So it's not so immediately clear that this is a character, but let me describe this in a different way, and this is going to be important. So let's say that I want to figure out what this is. So maybe I'll say alternatively. I'm gonna give you an alternative definition of a different way of saying the same thing. So what I claim is that all this character does is that it plugs in 1, 0, 0, 0, etc. So let's think about why this is the same thing. Suppose that I need to prove that this is true for all f, and as usual, it's enough to prove it for a basis, right? And so it's enough to prove it for the basis of monomial quasi-symmetric functions. Okay, so what is this? Let's say that if we plug in MC, then this is going to be the sum of xi to the xi1 to the c1 dot 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 up to xik to the ck, where I1 less than dot 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 less than ik. So this is the monomial symmetric function MC. Okay. Now what happens if I plug in 1, 0, 0, 0, 0? Well, you see, if your composition has 2 or more parts, then when you plug in 1, 0, 0, 0, no matter what term you choose, one of them is going to be 0, right? Because there's only one, and everything else you're setting to 0. Okay? So, I mean, in other words, does that make sense? So let me say it again. I'm going to take my monomial quasi-symmetric function, which looks like this, and I'm going to plug in the first variable is equal to 1, and the other ones are equal to 0. Okay? Look at what happens here. This is a term that is usually going to be 0 because it's, only x1 gets to be 1 and the other ones are 0. And so this is probably 0 to the c1, 0 to the c2, etc. The only chance that this has to not be 0 is if there's only one term and it is equal to x1 to the something. Because as soon as you have more than 2 variables, then this is going to have to be 0. Okay? So the only chance that this has to be non-zero is if C has only one part. And if C has only one part, it looks like this, then this is just the sum of xi to the n. And when you plug in 1, 1, and a bunch of zeros, you get 1 to the n plus a bunch of zeros. Okay? So that means that this equation is true for this basis, and therefore it's true for any f. Okay? And this provides me two different ways of thinking about it, and the good thing about this description is that here it becomes very clear that this is multiplicative, right? Because if you do this to f times g, you're just plugging in at f and at g the same thing. Okay? Okay. So these are so this is one important character that I want to consider on QSYM. Now, let me do this, a very similar thing for SYM. So these are the symmetric functions. In n variables. Again, the coproduct is given by the same formula. Okay? And here I'm going to do the same thing where my character here, I'm going to describe it in two ways. On a basis. And I'm going to use the same monomial basis, except that now the monomial basis is labeled by partitions lambda. And so this is going to be 1 if lambda is either empty or a single element. So this is empty. And 0 otherwise. And again, a different way of saying this is that I'm taking a symmetric function and I'm plugging in 1 for the first variable and 0 for the other ones. Okay? Let me emphasize. I've said it maybe 5 times already, but I'm going to say it again. I had a lot of freedom for each one of these things, right? So for each one of these Hopf algebras, I might have chosen a different character, and well, I would just get a different combinatorial Hopf algebra. But you'll see that the examples that I wrote down, I chose them carefully to illustrate a couple of points. Okay. Okay. So as usual, we just define a new algebraic object, and so the next natural step would be to define the morphisms between them. Okay. So what is going to be a morphism of combinatorial Hopf algebras? So let's say that you have one combinatorial Hopf algebra, let's say H and alpha, and you want to map it to maybe I and beta. Yep?
Yeah, I have a question. You might have stated this in the beginning already. So it seems like to connect algebra to combinatorics, a great way is through the character, or having a character,
Mm-hmm.
and as it is by definition. But is it possible that you can have a Hopf algebra without necessarily a character and talk about combinatorics?
Right. So a lot of what we've done today is very combinatorial, even if it didn't fit this definition. And so, but there is this notion of combinatorial Hopf algebra, which demands that you need to have a Hopf algebra and a character. Okay, and yeah. So in what I'm going to do today and in the next class, because I'm always going to be dealing with combinatorial Hopf algebras, then I need to say the character. But I agree with you that the combinatorics is actually more entrenched inside the Hopf algebra than in the character. I mean, a lot of these characters are pretty trivial. And the combinatorics is really stored more in the Hopf algebra itself. And more in, I mean, a lot of this is about how a lot of these Hopf algebras really are indexed. We have a basis indexed by combinatorial objects. I think that's what a lot of these have in common. And you don't see that anywhere in this definition, but maybe that's the psychological thing to think when you hear combinatorial Hopf algebra. Yep.
So I get that, like, sort of, quote unquote, most of the structure of that, like, makes up a Hopf algebra can be sort of thought of as existing as coproduct. But is there another way? Is there another reason that you're, like, reminding us of the coproducts here? Do these tie into characters somehow?
Yeah. So the question is, why did I write down the coproduct and not the product? And the answer is that I started because for graphs we've discussed two different coproducts, and I just wanted to clarify which I meant. And somehow I did it with the first one, and then I continued with the other ones. But I should have written the product on all of them, but I think the product is usually clearer, which is why I didn't write it. But I should have written the product. Okay, morphism of combinatorial Hopf algebras. So what should this be? Well, presumably you should take the Hopf algebra to the Hopf algebra, right? So it should be a morphism of Hopf algebras. So it should preserve the product, the coproduct, the unit, and the counit. Okay. But one thing that you'll notice is that combinatorial Hopf algebras come with a grading. And so we actually need to also make sure that this preserves the grading, okay, which doesn't hold for free. Preserving the grading. And so what that means is that if you take something homogeneous of degree n here, it should go to something homogeneous of degree n here, which usually happens in everything that we do. But so we need to preserve the grading. Connectedness is going to be preserved for free, but you need to make sure that you preserve the character. So okay, so f of h n should be a subset of in. That's what this means. And the character. And so what should this mean that f preserves the character? Well, it means this. So we have this map from h to I. Okay. F. And we have a map from h to my ground field, right, and this is called alpha. My first combinatorial Hopf algebra consists of H and this morphism. My second one consists of I and this morphism. Okay. And what I want is for this diagram to commute, which you can write as saying that, this in a different color. So the first condition was that f of hn should be an in. And the second condition is that alpha should be the composition of f and beta. Beta f. Right. So the question is, if you have a morphism of the Hopf algebras, can you extend it to the character? And you'll see actually you can't, because
Well, wouldn't you be able to do it
Right, so that's a good point. For example, if I choose the co-unit here and here,
And there's a morphism
then
of the Hopf algebras, then
then actually, by virtue of being a morphism of Hopf algebras, you have to have this diagram commute. So one example is to always make this and this the co-unit. That's right. But Zach is also right that you can't just choose these randomly and expect to find a morphism. Because if you have your morphism, which sometimes, I mean, often this morphism is pretty clear what it should be. Then once you've chosen beta, alpha is determined. Right? So is determined by the composition of f and beta. And so you can't very freely choose alpha and beta. Alpha and beta have to be very close to each other by, and the f tells you how to translate from one to the other. Okay. And somehow the idea with this is that this map is encoding some combinatorial information, and then you're going to push that combinatorial information over to this side through this map. Okay. So that's the general setup, and let me go ahead and state this very important theorem, which is the following. First, let me say it in kind of fancy category theory language, and then we'll translate it to English, or at least something more concrete. So when I was talking about this one, I said it was important, and it's somehow more important than the other ones, at least in some sense, because this is what's called terminal object in the category of combinatorial Hopf algebras. And actually, I shouldn't say a terminal object, I should say the terminal object. So somehow it's kind of the end-all of all combinatorial Hopf algebras. And what this means is that whenever you have any combinatorial Hopf algebra in your hand, you always have a unique way of mapping it to this one. So in something more English-like than this, for any combinatorial Hopf algebra, there is a unique morphism. Let me say there is a unique combinatorial Hopf algebra morphism to this special one. Maybe I'll call this, I think I called it psi here. Yeah.
For any choice of alpha?
Alpha is part of the combinatorial Hopf algebra. So if you choose H and you choose alpha, that completely determines this unique morphism. So you see what this is saying is that whenever you have any kind of, I mean, you should think what you have here is a combinatorial Hopf algebra with some combinatorial structure, and what this says is that you can always take the elements of this guy and send them to quasisymmetric functions. Okay, so this gives you a recipe, and it's not some creative recipe that somebody invented in a very clever way. It's the unique recipe that you must have invented because there's only one. There's one unique recipe to take elements of your Hopf algebra and turn them into quasi-symmetric functions. And so that means that any one of these things, we can transfer them into quasi-symmetric functions and try to use what we know about quasi-symmetric functions to study them. Okay. So is that statement clear? More or less, yes?
It's clear. It's unbelievable.
It's clear but unbelievable. Okay, I like that. Well, maybe I'll prove it and then you'll believe it. So. Okay, I'm going to give a proof of this. But yeah, this. I mean, let me say a little bit about the history, because the history is a little bit backwards actually. What happened historically is that in combinatorics there were a lot of quasi-symmetric functions around. So people define the quasi-symmetric function of a graph or of a poset or a matroid or these different things. People kind of saw some common features between these different quasi-symmetric functions. But this theorem really explains why it was inevitable to land the quasi-symmetric functions, because this is the terminal object where you should have landed. Okay. I should say that this is a fairly recent theorem of Marcelo Aguiar and Aguiar-Bergeron and Frank Sottile. And I'm forgetting what year this is from, but it's something like 10 years old, something like this. Okay. So I'm gonna give a proof of this. So what I'm gonna do is that I'm gonna construct psi, and I'm gonna prove to you that it was inevitable that that was the psi that I needed to choose. So proof. We have alpha from H to K, right? That's our character. And because everything here is graded, I can actually look at I can restrict that map to Hn. Okay, I can see where the things of degree n go, and I'm going to call this map alpha n. Okay? So alpha n is going to be some map from Hn to K. In other words, alpha n is just an element of the dual space to Hn. Okay? Now, what I'm going to do is the following. I'm going to say, I'm trying to construct a map from H to QSYM. Okay? But especially given that I put a star here, we always have in linear algebra this tool of duality, and sending a map from H to QSYM is the same thing as sending a dual map from QSYM star to H star. So instead of constructing from H to QSYM, I'm going to try to construct it the other way around. Construct a dual map. And one reason that that's an advantageous point of view is that we know what QSYM star is, because remember that the dual of QSYM is NSYM. Yeah? So, okay, so recall that the dual of QSYM is NSYM. And just to remind you, NSYM is just this Hopf algebra freely generated by H2, H1, H2, H3, etc. And these are things that don't commute with each other. And this guy has degree 1, degree 2, degree 3, etc. And since these guys generate NSYM and generate it freely, then I have a unique map from n sim to H star. How do you define a map from n sim to H star? Well, the thing is that we have free generators here. And so all I have to do is decide where the generators go. So where should I map the generator Hn? Well, I only know one. This is supposed to be a homogeneous map. It's supposed to preserve degree, so I need to send this to something of degree n. What do we know of degree n here? The only thing that we know in Hn star is this element. And so if you're going to define this map, presumably this is what you're going to try to do. Okay? So I define it on the generators like this. And because these guys generate n sim freely, that means that this actually is a map of algebras. Now, it is important here to say it's a map of algebras because we took it like this and then we extended multiplicatively, but we haven't talked about the coproduct, and that's not something I'm going to talk about yet. But really, I'm going to want this to be a map of Hopf algebras. And so far, I don't know that because I only know this is free, and so it's free as an algebra, and therefore I can define a map of algebras. Okay? But that'll do for now. We'll see how to deal with that in a minute. But then the point is that I can, let's give a name to this thing. Okay. And this gives me a dual map. A dual map from the dual of this guy, which is H, to the dual of this guy, which is QSYM. And I'm going to call this thing psi. Okay. And I would argue that this at least has a chance of working, because we're mapping from the correct thing to the correct thing, and it is, by the way, this is a dual map of what? What kind of morphism is this? This is a map of algebras, right? So when you take the dual of a map of algebras, you get a map of coalgebras. So we know that this map at least preserves the coalgebra structure. And we did pay attention to alpha to construct this, which is important, right? Because that construction is supposed to depend on the character, and this construction depends on alpha. Okay? And I'm going to show that this is it. This is the unique map. Okay, so and actually, I want to compute it more explicitly, because this is not only an existential statement, but it actually gives you a formula for this guy. So what does duality mean? Duality means that if I take, okay, so this should look familiar to you guys. Phi of, let's say phi of h, well, okay. Phi of f comma g should be equal to f comma phi star of g. That's what it means for these maps phi and phi star to be dual. Now, what are these inner products? Where does this live? Phi of f lives in h star, and so here I should say f lives in n sim, right? And then phi sends it to h star. and G lives in H, and phi star sends it to QSYM. Okay? So this is just the pairing between the Hopf algebra and its dual, and this is the pairing between NSYM and QSYM, which are duals to each other. Okay? Now let's see what this means for a basis of NSYM. And so what is a basis for NSYM? Well, given that NSYM is the free algebra on these things, that the basis that we like is just these H alphas. HC. So C here is a composition, and HC just means HC1 up to HCK. So what does this say? This says that phi of HC comma G is equal to HC comma phi star is called C of G. Okay. Okay. Oh, and what is phi of HC? Well, phi is multiplicative, and so HC gets mapped to alpha C. So this is alpha C of G equals HC of C of G. And let's write down what alpha C is. Here, alpha C is equal to alpha C1 dot 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 alpha CK. Okay? Now, let me write this a little bit differently. Let me plug in so alpha C is the product of the different alphas. But where is this product taking place? Well, you see, this alpha C1 up to alpha CK, they're actually elements of H star. And so this is actually, this multiplication is actually taking place in the dual Hopf algebra. And so remember, what are you doing when you're multiplying in the dual Hopf algebra? What you're doing is you're co-multiplying in the main Hopf algebra. And so this is just going to be the sum over the coproduct of G, and then you apply alpha C1 to G1 dot 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 alpha CK to GK. Okay. That's what this alpha C is. Okay. Now, let me okay, there's two things that I want to do, so maybe I'm going to leave space for a little computation here. But I'm in the process of finding a formula for phi, okay? And so for C, I'm sorry. So C of G. C of G is what? Well, remember, C is supposed to send an element of my Hopf algebra to a quasisymmetric function. Okay, so C of G is a quasisymmetric function. It lives in QSYM, and so let's say that I write it in terms of a basis. What basis do we like for QSYM? What is your favorite basis for QSYM? I see Krista saying M, and then saying, is it M? It's absolutely fair. So there's too many bases around, but M is the monomial basis is somehow the easiest for this. For QSYM, we've seen two different bases, M and F. The monomial one, and then F is this other thing, which you'll be acquainted with in your homework a little bit better. M is the easiest. And so let me just write phi of g in terms of the M basis. So it's some linear combination of m's. Let's say the coefficients are, I don't know, AD. Okay. Then what is this equation? Well, what is HC comma phi of g? This is equal to HC comma sum over the different d's of AD comma, sorry, AD and D. Okay. Now, the other thing to remember here is that we discussed how NSYM and QSYM were duals to each other. They were duals. And the dual basis to the H basis was the M basis. So one thing to recall is that because these bases are dual to each other, this is going to be 1 if C is equal to D and 0 otherwise. This is the duality of NSYM and QSYM. And so that means that when I take this, all I get is almost everything dies, almost everything disappears except the MC term, which is going to give me AC. Okay? So AC is equal to HC comma phi of G. Okay? And so, okay, I have a string of equalities here that I'm gonna put together. First of all, alpha C comma G this is the same thing as alpha C of G, right? These are two different notations for the same thing. This is a linear function acting on an element. We can write it like this. That's how we did it here. It's equal to this, which is 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 equal to this. Right? So what do I have? I have phi of G is equal to the sum over all the different D's of AD and D, where AD is given by that. Alpha D of G M D. So I don't know, this is some formal computation. The point of it is that if you wanted to know what I told you that this theorem gives you a recipe for any element of your Hopf algebra. It sends it to a quasisymmetric function. And the way it does it is like this. Here's your element of the Hopf algebra, and here's your quasisymmetric function. It's given in terms of the monomial basis. And the coefficients are given by alpha, because alpha is the character that is part of this. And alpha is defined like this. Okay? So alpha C of G is given by this. Okay? And so the point is that this is a completely explicit recipe for the homomorphism. And I know right now it's a lot of symbols, but what we're going to do is look at some examples and see what this actually does, and we'll see that it's very combinatorial. Okay, so far, I started with this definition and I gave a formula for C. Now, what do we know about C? Maybe I don't want to erase this just in case I need it. What do we know about C? We know that C is a map of coalgebras. By our construction. it's not hard to check that C is also a map of algebras. Okay. What do you have to do to check that? You have to check that C of G H is equal to C of G C of H, and that's something you can write out and compute it, and you'll see that it checks. Okay. So this is a map of Hopf algebras. Why is it graded? Because we started with these graded things where Hn, which had degree n, was sent to alpha n, which had degree n. And so this map is graded, and therefore the dual is also graded. So it preserves grading. Okay. So it preserves the grading, and the last thing we have to check is that it preserves the character. So how do I know that the character is preserved? I need to check that this diagram commutes. Okay. Now I'm going to check that this diagram commutes. Given that this is graded, I'm going to just check it in degree n. Okay. So that's what I'm going to do over here. So here's Hn. Now I'm mapping this to I, which is QSYM n. Okay, and this is my map C. So the map from here to here. Okay, so let's take an element here. Let's say G. Okay. So when I send it over here, it ends up being C of G. Okay. And when I send it over here, it ends up being what? Hn to K. This is the map alpha n, right? This is the map alpha n. And so right here, I get alpha n of G. Okay. Now, what happens when I map QSYM to K? What is that map called? This map is that map theta Q over here, but restricted to degree n. Okay? And what does this map do? This is the map that lets the monomial m sub n survive and kills every other monomial. Okay? So what is the thing that lets n survive and kills everything else? Well, because m and h are dual bases, this map is precisely called Hn. Okay? And so when I take G to phi of G and I map it over here, I'm going to get Hn of phi of G. which is this, right? It's exactly this equation. Alpha n of G equals, I mean, if I plug in C equals n, I get that alpha n of G is Hn of phi of G. And so that means that this preserves a character. Okay. And so that gives me a proof that this really is a combinatorial Hopf algebra. Okay. But by seeing this coincidence that just happened, that the equation that I wrote here was exactly what I needed to commute here, you can backtrack everything. And you can say, if you happen to have a combinatorial Hopf algebra morphism, then this must have commuted. And if this commuted, this equation must have been true, which means this is true, this is true, this is true, this is true, this is true. And you can reverse it, and you'll see that you have to be dual to this map. Okay? And so this wasn't just a clever choice. If you start from the definition of this diagonal commuting, you'll see that you arrive at having to be dual to this map. And so that's why not only is this correct, but it is uniquely correct. This is the only morphism that exists. Okay? Okay. So this is the proof of the theorem. And well, it's a little bit involved, and I like that it brings together several of the ingredients that we have been developing over the last couple of weeks. Yeah.
I think you said before in previous lectures that like if you study Hopf algebras, you're always going to see like quasi-symmetric, symmetric Hopf algebras. Is it because of the structure that it has and proofs like this that it has?
So this, yeah, I mean this explains why quasi-symmetric functions are going to appear all over the place. Whenever you have a Hopf algebra and a character, then automatically you know that behind this thing is lurking, because this is a unique morphism that exists and is uniquely defined. And by the way, as Alejandro mentioned earlier, we always do have a canonical choice of character, which is to choose the co-unit here. So we always have a character. We always have at least one choice of character, which means that we always have at least one quasi-symmetric function as soon as you are graded and connected, and your dimensions are finite in each piece. And so this explains why QSYM appears all over the place, basically. Quasi-symmetric functions appear a lot. Okay. Okay, so that's a big statement, and now let me make another big statement, which is that suppose that your Hopf algebra is co-commutative. Okay? And let's say that we try to do the same thing, but we restrict ourselves to co-commutative Hopf algebras, which, if you look at it, a lot of the Hopf algebras that we have studied are co-commutative, maybe including every single one that I had here. Not all of them, but I think 5 out of 6 of the ones that I had were co-commutative. So maybe I'll just let me find a red pen, and I'm going to change the statement here to say that if you focus your attention to co-commutative if you only look at co-commutative Hopf algebras, and you look at that category, it turns out that this is the terminal object. QSYM is not co-commutative, actually. If you let's take that comment to the forum. But if you look at the co-commutative combinatorial Hopf algebras, then this is going to be the terminal object. Okay? And so what that means is that if you have any co-commutative combinatorial Hopf algebra, then there's going to be a unique morphism now to SYM. Let me, instead of scratching this off, maybe I'll just write SYM with actually its character sigma zeta s. Okay? So if it's co-commutative, then what you should put here is SYM and zeta s. Okay? And the proof is going to be exactly the same. The thing is that if this is co-commutative, then the dual is going to be commutative. And so I need to do exactly the same thing, except that I need to put commutativity here. And when you put commutativity here, the algebra that you get is precisely symmetric functions. So, okay. So that's, and I should say that the formula is also the same. Okay? In fact, let me write it down. The formula looks like this. So let's say if H is co-commutative, then I have C from H to SYM, and this map is given by C of H is equal to what I wrote there, except that now instead of adding over compositions, I add over partitions. I get alpha lambda of H M. And now this needs to land in SYM, and so here the monomial symmetric functions are called like this. Okay, so this is the quasisymmetric function where alpha lambda of H is equal to the sum over the coproduct of H of alpha lambda 1 of H1 up to alpha lambda k of Hk. So lambda here is lambda 1 up to lambda k. Okay. So let's see what this looks like for some examples. So let's talk about graphs. It's a nice concrete example. Hopf algebra of graphs. But I want the co-commutative one that I just considered, where delta of G is the sum over the subsets of the vertices of G restricted to W tensor G restricted to V minus W. Okay. So this general recipe tells me that for any graph G, I'm going to get a quasisymmetric function. Actually, because this is co-commutative, remember, co-commutative means that if you flip the order here, you get the same thing. And here, clearly, you do. Because this is co-commutative, then I apply the red version of that theorem, the co-commutative version, which says that I get a unique symmetric function. Which is going to look like C of G, and this is going to be equal to the sum over all the different partitions of lambda. Let's say that G has n vertices, okay, and therefore here, what I'm going to get is partitions of n. Yep.
Can we change that I to a U? It looks like a restriction sign.
Yes. For any graph G on n vertices, we get a symmetric function, which looks like this: sum over lambda in n of, and then I get sum over the coproduct of G and I get alpha lambda 1 of G1 dot 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 alpha lambda k of G k. Okay. M lambda. This is what I get, right? Now, we have to remember what alpha is here. So remember that alpha in this case was just the, here is just the character, right? And actually, let me call it, sorry, I meant it's just the co-unit, which is 1 if G has no edges and 0 otherwise. And let me emphasize that, and let me actually put epsilons here so that you realize that this is the most trivial choice that I could have made, but also the maybe the most canonical. I mean, a Hopf algebra comes with a co-unit, and that's what I'm going to feed into this machinery. Now, what do we know about co-units? We know that co-units kill almost everything, right? It's only the trivial stuff that survives. So actually, even though this is really messy, almost everything is 0. So if you don't want to be 0, then what has to happen? What has to happen is, let's look at this term. When is this non-zero? And by the way, what is this? What is the coproduct here? We're just taking the graph and splitting it into k parts, right? So here, all I'm doing is taking my graph G and splitting it into k parts. 1, 2, 3, up to k. Okay. Now, this is going to be non-zero when? First of all, I need that every one of these graphs is trivial. So G I has no edges. Right? And what else needs to happen? This is the map of degree lambda 1. And so I need G of 1 to have lambda 1 vertices, etc. Lambda I vertices. So what am I doing? I'm just taking my graph and cutting it up into pieces where the ith piece has to have lambda I vertices, and each piece cannot have two vertices that are connected. Okay? Now, what if instead of thinking of I as a number, I think of it as a color? So I have a graph. And now I'm separating the vertices into I groups, into k groups. And I'm going to call these colors. Color 1, color 2, up to color k. Okay? So sum over the colorings of the vertices with natural numbers. What do these colorings have to satisfy? Well, you have to satisfy that if you have two vertices of the same color, then they can't be connected by an edge. So you might know that this is exactly what's called a proper coloring of a graph, right? Because you never want to give two connected edges the same color. Okay. So what we have here is precisely the proper colorings of a graph. Proper colorings of my graph K of G. And by the way, this is non-zero in this case, and if it's non-zero, it's 1, right? Because this is just a bunch of 1s. So really what I get here is just number of proper colorings of G with lambda I vertices of color I. And proper means that neighbors get different colors. Neighbor vertices get different colors. Okay? And M lambda. What is M lambda? M lambda is just a, putting a bunch of monomials with all the different values of the xi's. Okay? So actually, what I'm going to get in the end is just the sum over the proper colorings of my graph with natural numbers of what you might call x to the coloring. Okay, and this is my symmetric function, which actually is usually denoted x sub g. So for example, if I have a graph like this one, and let's say that I color the vertices, okay, so if I use color 1 here, then I can't use color 1 here, so let's use color 3. Here I can't use 1 or 3 because they're neighbors, so I'll use 2. Here I need to use a different one, so maybe I'll use 5. Maybe I'll use 2 here. I'll use 3 here. I'll use, let's use 1, and I'll use 2 here. This is a proper coloring, and it gives me a monomial x to the kappa, which is just saying that I use the color 1 twice, the color 2 3 times, the color 3 twice, and the color 5 once. Okay. So this is what the theory spits out, and it's inevitable that this is what comes out. Okay. And this thing was called Stanley's